K is a positive real. N is an integer greater than 1. N points are placed on a line, not all coincident. A jump is defined as follows. Pick any two points, A and B, which are not coincident. Suppose that A lies to the right of B. Replace B by another point B' to the right of A, such that AB' is equal to K times BA. For what values of K can we move the points arbitrarily far to the right by repeated jumps? This is problem number 3 from 41st International Mathematical Olympiad, the hardest of that year. I came across this problem in my school years participating in that Olympiad. I didn't manage to solve it within Olympiad time, I solved it further, and it took me more than a week of hard thinking. I was extremely fascinated by its solution and hope to share this fascination with you in this video. The text of the problem is on your screen, and I prefer, before considering general case, to start with some simple examples. Let us take n equal 2 and look what happens in this case. It's very simple, so I recommend you pause the video and try it by yourself before you keep watching. In this case, we have just 2 points, so each jump is uniquely defined. If k is greater or equal than 1, then the distance between points is non-decreasing. That is, it either increases or remains constant. Clearly, in this case, we can move points as far to the right as we want. But what if k less than 1? Let us denote initial distance between points as x. After first jump, it equals kx, then k square x, and so on. The total shift from initial position is the sum of geometric progression, x times 1 plus k square, and so on. Well-known fact is that for k less than 1, this sum is convergent. It never exceeds x divided by 1 minus k. This means that there exists a threshold point which never will be overjumped. So for n equal 2, the answer to the problem's question is k greater or equal than 1. For n greater than 2, you have many ways of selecting points. For example, you can always jump leftmost point over the rightmost one. Or you can select 2 points and make several jumps with them. Then select another 2, and so on. Or you can select points at random, without any strategy. Which one is the best? The complete and exhaustive solution of the problem must contain answer, explicit set of k values for which points can jump infinitely to the right. Let us call them good values. Proof that these values are indeed good. You must provide jumping strategy and show that it works. Note that if there are many working strategies, it is enough to provide only one of them. This part is called sufficiency. And proof that other values are bad. Points cannot jump far away, whatever strategy we use. This part is called necessity. The first step of solution is try to guess the answer, even without proof. Let us again remember what happened for n equal 2. Here we had some special value of k, equal 1, which was the minimal good value. For this value, the distance between points remained the same after each jump, so the picture was strictly periodic. Now it occurs that similar example exists for arbitrary n. Try to find it. Locate points so the distances between neighboring points are equal. Let leftmost point jump over the rightmost one so that this equidistance persists. Appropriate value of k is evidently 1 divided by n minus 1. This is a hint that maybe 1 divided by n minus 1 is minimal good value. But currently it is proved to be good for only this particular location. Will it work for other locations? Let us prove it for n equals 3. So we take k 1/2 and 3 arbitrary points. We will use the two-point sequence strategy which was already illustrated earlier. Of course, first I recommend you try it by yourself. We select 2 points, B and C, and make several jumps with them until they almost coincide. Denote distance AC at this moment as D. Now points A and C jump until they almost coincide. Due to sum of geometric progression, the new distance BC will also equal D. Well, not precisely, but we can make it as close to D as we want. Repeating this procedure, we can move points as far to the right as we want. You can carry out some more experiments, and all of them will hint you that the answer is k greater or equal than 1 divided by n minus 1. However, this is only a guess. Currently it is absolutely unclear how to prove it. In problems like this, often method of invariance occurs helpful, or as I prefer to call it, method of trace functions. A well-known example in physics is energy of closed system. As the system changes, its total energy remains constant. Another example, entropy, is not strictly speaking an invariant. It can change, but only in one direction, only increase. This is the so-called semi-invariant. For those who is not familiar with this method in mathematics, a very simple example. Consider a number 2025 written on a board. An operation is allowed. Select two neighboring digits and increment them both by 1, or decrement both by 1. Of course, you can increment them only if they are less than 9, and decrement only if they are non-zero. Is it possible to obtain reversed number 5202 by these operations? You see that there is wide diversity of numbers which can be obtained, but 5202 is not among them. After many unsuccessful attempts, you may suspect it is impossible. But how to prove it? Let us introduce trace function s, which for any numbers with digits a, b, c, d, calculates a minus b plus c minus d. Applied to our initial number, it gives minus 1. This value does not change after described above operations by absolutely clear reason. Increments of neighboring digits cancel each other. But for our target number, the value of s is different. So it is not achievable. After this introduction, you can guess that we are going to do something similar in our jumping points problem. Find some trace function. But function of what? In previous example we had a number whose digits changed, and these digits were arguments of function. What are the arguments in our case? The only numbers related to point locations are pairwise distances between points. So exactly them we are going to use as function arguments. But currently this is the only thing we know about the function. Its explicit form and how it should work is completely unclear. Now consider again the example with 2 points. The distance between points has a semi-invariant property. It always changes unidirectionally. If k is greater than 1, it increases, and if k is less than 1, it decreases. We want to find something similar in general case. That is, the function s, which we are looking for, must satisfy following conditions. As we said, it must depend only on current pairwise distances between points. And after all jumps, this function must change unidirectionally, always increase or always decrease. Direction of that change, increase or decrease, should depend on values n and k, but not on how points are located or which jumps we use. However, if you try to find such function, you will fail. It turns out that the function which exactly satisfies this condition does not exist. Try to understand why and try to guess how to slightly modify the condition to make it solvable. Let us more carefully consider three-point case. There are three alternatives for each jump: left over right, middle over right, and left over middle. In first two cases you can see that total spread of points increases. They become more widely located along the line. And in the third case they squeeze to each other. So looks like this kind of jumps is less profitable. This is also confirmed by examples in the beginning of the video. Here first two strategies contained only jumps over the rightmost point and looked working well. And the third one contained also jumps over interior points and looked worse. Of course, this is again only a guess, not a strict proof. But this observation gives us a hint how to change the condition of a function. We must consider only jumps over the rightmost point. And now I guarantee that this way defined function exists. Finding it is not easy. Actually, it is the most difficult step of the problem and 90% of solution. Of course, I recommend you try it by yourself, but before, let us for clarity consider some wrong examples. In the first example, let S be the distance between leftmost and rightmost points. Consider point locations with distances between them as shown. If point B jumps over E, this distance increases, and if then A jumps over B, it decreases. S does not change unidirectionally and thus does not satisfy semi-invariant requirement. Another example. Let S be product of distances between neighboring points. Pause the video and find counterexample by yourself. Here it is. Jump with decreasing S and jump with increasing S. So this S function also is not valid semi-invariant and does not suit us. And now I warn you that finding this function is the most difficult step of the problem and 90% of solution. If you want to perceive the whole intrigue and pleasure of the problem, stop the video right now and try it by yourself. And I am going to tell the answer in 3, 2, 1. The true S function, which satisfies all requirements, is sum of distances from the rightmost point to all the other points. Maybe you are disappointed now because you were expecting symmetric function. But this is part of problem's difficulty. Standard symmetric functions do not work here. Let us prove that this function really suits us. Let Z be the rightmost point and D be one of the others. Denote distance from Z to D as D and some of other distances as x. So initially we have S equal x plus D. Now what happens when D jumps over Z? Distance D is replaced by KD and all the other distances increase by KD. So we have new value of s equal to x plus n minus 1 k times d. The difference between new and initial value of s, we denote it delta s, is d times n minus 1 k minus 1. And now we see that the sign of this difference depends only on the value of n minus 1 k minus 1. If it is positive, value of s increases, and if it is negative, value of s decreases. Isn't it absolutely gorgeous? Even now, after more than 20 years, I am fascinated explaining it. But what then? The problem is not still solved, despite the most difficult step is done. How this s function is related to the problem's question? You can again pause the video and try it by yourself. I recall, the question was for which values of k points can move infinitely to the right, and I claim we've just got the answer. The first two inequalities we just obtained can be solved with respect to k and gives k greater or equal than 1 divided by n minus 1. This is exactly the set of good values. For these values of k points can jump infinitely to the right, and for others they can't. The only thing remains to do is to prove this statement. Let us start with sufficiency. This is the easier case. We denote by delta x the distance between rightmost points after jump and before jump. We call this distance total shift of the set of points. You can imagine this set as a train which moves to the right when a jump occurs. Denote also by d the distance between leftmost point and rightmost point. A very important inequality takes place. D is greater or equal than s divided by n minus 1. Let us understand why this happens. A well-known and easy-to-prove lemma asserts that maximum from a set of numbers is not less than average mean of that set. This is exactly our case. There are n minus 1 distances from the rightmost point. Their average is exactly s divided by n minus 1, and their maximum is d as we just denoted. So, the inequality consequently holds from this lemma. Finally, denote by S0 the value of S at initial moment of time when jumps didn't start yet. Due to the case we are considering, at any further moment of time, value of S will be not less than S0. Now we propose strategy according to which the leftmost point will always jump over the rightmost one, and prove that it works. Indeed, using notations introduced above, we get series of inequalities. Delta x is equal to kd, which is greater or equal than ks divided by n minus 1, which in turn is greater or equal than ks0 divided by n minus 1. But hey, this number is a constant. S0 is fixed number because it is the value of s at the start, so we found the lower bound of total shift, positive number such that delta x is always greater than it. Hence it's evident that repeating such jumps we can go as far to the right as we want. Necessity. In this part we must prove that for k less than 1 divided by n minus 1 there exists threshold point never overjumped. You may ask, isn't it proved already? S decreases for these values of k, so points more and more squeeze to each other. Their jumps get shorter, maybe not monotonically, but eventually they go to 0. Doesn't it mean that points are restricted in finite area and cannot jump far away? If you are not experienced, this may seem clear and evident. However, in mathematics often evident things are wrong. Here is a well-known example of a harmonic series, sequence of numbers, which decrease to 0, but their sum is infinite. This shows that the only fact of decreasing delta x doesn't prove anything. Some more strict argumentation is necessary. To obtain this argumentation, we'll write a gain equality for delta x. Notation of delta x, total shift, comes in handy again and denotes the same as in previous part. And d this time is not maximal, but arbitrary distance from the rightmost point to any other. Nothing unusual so far, this equality is evident. But let us write below another one derived recently when we analyzed change of s. Delta s is equal to some constant coefficient multiplied by d. You guess what happens now? From these two we infer the third one, the main equality of the problem, which is absolutely brilliant. Delta x is proportional to delta s. I recall, delta s now is negative and the coefficient is also negative, so right part is positive and equality is correct. And it shows that how much we move to the right, proportionally so much we lose in s. And now we can provide exact position of threshold point. Let again S0 be value of s at initial moment of time. Summing up all shifts and all delta s, we obtain a very nice inequality. Sum of all shifts is not greater than S0 multiplied by the same coefficient. This distance, measured from the rightmost point, can never be exceeded whatever sequence of jumps we use. And this completely finishes the solution. Well, not completely. There was a little trick, which is actually a huge drawback. We restricted ourselves only to jumps over the rightmost point, and the statement that these jumps are better than others was only a guess without a proof. So strictly speaking, not all possible strategies are considered and the solution cannot be regarded as complete. But now we have tools to get rid of this restriction. I only give you a hint and recommend you to finish it by yourself. If jump occurs not over the rightmost point, the brilliant equality which we obtained, the main equality of the solution, is replaced by a less or equal sign. This leads to less or equal sign in the next chain. These are the only changes. The conclusion and threshold point remain the same. Now the solution is complete. The last part of proof, necessity, is so much fascinating to me. I want to emphasize it again with some real-life illustration. This is the train. And this is cheese, exactly 1.5 kilograms of perfect Georgian Sulguni cheese. After each jump, the train goes forward, and some amount of cheese is consumed proportional to the distance covered by train. For example, let the train shift after the first jump be of 1 kilometer length, and weigh it up 60 grams of cheese. The next jump gives 2 kilometer shift, which costs us 120 grams of cheese. Then is 0.55 kilometer, 33 grams, and so on. This proportionality strictly holds along the wall motion. How long is the distance the train can go from initial point? Any junior school student will answer. 1,500 divided by 6t is 25 kilometers. Of course you guessed, this cheese is exactly our s function. This is why I think this problem one of the most beautiful from IMO. The core idea is so simple you can explain it to a little child, but unraveling it from initial problem requires years of mathematical training. If you agree with me, my goal is achieved. Thanks for watching.